Hello everyone, Stuart Mason here with Math 156, Script 5b. We're going to be talking about some well-understood theoretical sampling distributions for continuous random variables. So the first is topic number 1, where we're going to be exploiting the fact that the sampling distribution for an exponential is a gamma. And so this is nice because it means that if we know something is exponentially distributed, or we believe something is exponentially distributed, and we want to make estimates about its rate parameter, we can use the fact that if it's exponentially distributed, then sums of those draws will be gamma distributed to allow us to make some estimates on sort of confidence intervals around the range of what the lambda parameter is, or we could check the assumption as with the hypothesis test. Is the rate parameter what we think it is, or is this data distributed exponentially? So helpful fact, and we're going to explore it a little bit in detail here. So first we're going to recreate a figure from the textbook, which is a nice curve of the density function of an exponential with lambda 1 over 15. So as usual, this is one of ours helpful distribution functions. So this is density exponential. We're going to say x is a dummy variable running from 0 to 100, and compute the density given a rate parameter of 1 over 15. So this is going to give us a mean of 15. There it is. This is a figure that you can also find in the textbook. And now we can simulate sampling from this. So we're going to say for 1,000 times initialize some vector to store the results in. Give us 100 random exponential draws with the same rate parameter of 1 over 15. So this is going to be a vector 100 elements long, continuously distributed around 15. So let's do this. And we stored 1,000 of those means in the myMeans variable, and now let's make a histogram with 30 breaks. And this prob equals true argument is what tells it to do frequencies instead of counts. So we have density on the left here, and here's the probability of observing each of these different means. And you see it's sort of bell-shaped, although it's got a little bit of a lopsidedness to it, which is how gamma distributions tend to look. And since we know it's a gamma distribution, we can actually add the curve directly over it. So because we have 100 exponentials that we're adding up, the shape parameter of the gamma becomes 100. And the rate parameter, intuitively or nicely, stays the same. And we're going to color this in red, and this add equals true argument has the curve drawn on the histogram instead of replacing it. There it is. Now I'm going to talk a little bit about these factors of 100 that Paul put in, because I actually had to look at this code for a little bit and puzzle it through for why this was the case. So the reason he multiplies the x by 100 is because here x is running from about 10 to about 20. These are means. So these are the sum of the exponentials divided by the number of observations. There were 100 observations each time, so a mean of 14 means that the sum was actually valued at 1,400. And that's why he needs to put 100 times in here, because really these gamma variables are actually much higher valued than what's reported here. The reason why he has to multiply the y-axis by 100 is a little bit more subtle, but basically this 100x multiplication factor here can be thought of as compressing the x-axis, right? So over here, this used to occupy 800 x units, and now it only occupies 8 x units. Remember, the area under this curve always has to be 1, because it's a probability distribution. And so what that means is if we're squishing the number line together on the x-axis, we have to be stretching the y-axis by the same amount in order to preserve the area. Right? So think of them as infinitesimally sized rectangles, each with some given unit area. If you cut that width in half to preserve the area, you have to double the height. Similarly, if you squish the width down into a space 1/100th of what you started with, you have to 100 times the height, and that's why these two factors are here, and that's why they give you this very nice looking curve. So just to sort of illustrate their importance, let's take away the height correction, and you see we get this tiny thing down here. And if we took away the width correction, we'd get something that barely even makes sense, because we have these very rare probabilities here that are at the 12, 14, 16 area. But so anyways, that's sort of an explanation of why these 100x factors here are important. Of course, we don't need to do a for loop and sum over the exponential distribution. We could also just draw directly from the gamma. So we're going to say, give us 1,000 draws from a random gamma. The shape's going to be 100 because we're summing 100 exponential variables, and the rate of each of them is 1 over 15. And then we divide by 100 because we're taking the mean of these sums. So there's the resulting histogram of that. these two histograms ought to be equal up to random chance of the fact that we're just taking a sample. And now Paul shows us a clever way to overlay the histograms with transparent colors. So first, the key to this seems to be this RGB function that he's using. So let's call up the help. So it looks like each of these are the intensities of the red, green, and blue values, and then this final value is the alpha. Alpha is a common variable in graphics. It takes on values between 0 and 1. 0 is completely transparent, and 1 is completely opaque, and they're additive. So if we start with a quarter transparency, in places where there are two things together, we'll have half transparency. So let's plot both of these, and you see we get something that's blue but transparent, and something that's red but transparent, and in areas where they occupy the same space, it's a little bit darker, and it's a sort of pleasant purple blending of the two colors. And so now you can see reasonably well how the two histograms overlay, where purple is deficient but blue is not, and where blue is deficient but purple is not. We can do something very similar for the quantile plots. So in this case, we're actually going to store the result of these QQ norms in a variable, and this plot.itFalse is going to prevent it from drawing it to the graphics device. This range function will return the min and max of every vector you give it. So this is all the x points in the Q1 variable, this is all the x points in the Q2 variable, and so the range will give us the min x and max x observed in both of them. Similar argument for y, and type equals n is the plot function's command for don't plot anything. So this is basically just going to set up our axes with the range we need. And then Paul uses the points functions to manually draw in the Q1 points with a similar RGB trick as before, and then he draws also the Q2 points, and you get this nice sort of ghosted quantile plot. Now, I think that this, by default, QQ norm plots against a normal. So that's kind of why there's a little bit of aberration away from the means, because gammas aren't truly normal, although when you have such a high shape parameter, thanks to the central limit theorem, they do become approximately normal. I do think you can actually pass a gamma density function to this QQ norm function, and it will instead use gamma, but I'll leave that as an exercise to the viewer. So now we're going to turn to what I think is conceptually even simpler, and that's this already proven result that the sum of a Poisson distribution is itself another Poisson distribution. So we're going to be doing an experiment, looks like 10,000 times, and basically we're going to use this R plus function to get 10 random draws from a Poisson distribution with parameter 2. So if you run this once, you see, sure enough, a vector of 10 values, and you get 0s, 1s, 3s, and 2s. Infrequently, you even get a 5. And we're going to add them up and store the results 10,000 times. Now, Paul first calls the mean of this, which ought to be an estimate of the lambda of our resultant summed Poisson distribution. I'll give you a minute to think of what you guess that's going to be. I got it backwards when I first tried this. Okay, time's up. I guessed 4 because I thought, oh, yeah, we're summing 2 things with a rate parameter of 2, but of course we're actually summing 10 things with a rate parameter of 2, so the result should be around 20. And in fact, improbably, we got exactly 20. That's so surprising that I'm actually going to run this code again just to show you that it's not always going to be 20. That is kind of a funny moment, though. I'm glad I caught that on camera. And we can take a bar plot, and now we've got every possible mean that resulted from our experiments. And you see that it's, again, it's normal-ish because of the central limit theorem, although it's got a little bit of an aberration, and that's because it's truly Poisson. And also, none of these are non-integers because they're all sums of integers, and so that's also how you know it's not really distributed normal, it's distributed Poisson. Again, Paul does it the fast way next. He says we can actually just draw 1,000 samples from Pois 20 because the sum of 10 Pois 2 is Pois 10. And we can, again, overlay the bar plots. I'm sorry, this time we're going to put those side by side. And you see that, yeah, they do come out pretty similar, but not the same because of random sampling. You also got this warning message, which is not deterministic. It only happens some of the time. And this is because it's complaining that the columns of these two tables are not quite the same. So if we just look at table.mysums, you see it goes from 4 to 39. If you go from table Poisson sample, it goes from 6 to 39, and the reason for this is because values so far from 20 are quite rare. So for my.sums, we got a little bit fortunate or unfortunate, however you may interpret it, and we have a 4, unlikely. In percent.sample, we didn't get the 4, although we did get a 6, which is also unlikely, so unlikely it didn't occur here. So basically, that's the fact that these rows don't match up is why rbind is complaining. I have thoughts on how to fix this, but it's a little bit acrobatic. It's not really simple enough to warrant discussing it in this video, but if you're curious, send me an email and we can talk about it. Topic 3 is pretty fun. So here we're going to be talking about taking the mean of samples from a normal distribution and how the result of that is also normal. So rnorm2, this is a pretty simple function call. If you call rnorm with just one argument, it will give you a standard normal of that many draws. So rnorm2 is going to give us 2 draws from n, 0, 1, and then we sum them up. Here's a histogram of the result. And we know that the sum of 2 normals is itself a normal, which has as a mean some of the means, and as a variance some of the variances. So in this case, it should be mean 0, variance 2. Dnorm expects a standard deviation, so that's why Paul says square root 2. And you see the result very nicely approximate the histogram we got. But if we take the sample mean, we're not going to quite get exactly 0 and 2, although we did get exactly the theoretical mean before, so anything is possible. And as we proved, I think in week 4, you can even sum from different normal distributions. So if you have sample mean 4, variance 9, and you add from distribution sample mean 6, variance 16, the result ought to have mean 10, variance 25. You see here we have to actually dress up the rnorm calls a little more. So we say it will give us 1 draw, mean 4, standard deviation 3, variance 9. Give us 1 draw, mean 6, standard deviation 4, variance 16. And we add them together and store them. Here's a histogram. Here's the theoretical distribution. And you see it's a little bumpy, but it does nicely approximate it. And again, the estimates. So not quite 10, not quite 25, but in the neighborhood. Cool. Hope this was helpful, and I'll see you guys on Wednesday.